In thermodynamics, the energy possessed by a system is internal energy, usually denoted by U. The internal energy of a system is the macroscopic thermodynamic variable that changes when it either emits or absorbs heat energy. For example, ice at 0 degrees Celsius converts to water at 0 degrees Celsius by absorbing heat energy. Though there is no change in the temperature, the internal energy of ice increases when it is converted to water. On the other hand, if water at 30 degrees Celsius is heated to water at 60 degrees Celsius, both the temperature and internal energy of water increases. At a microscopic level, the internal energy of a system is defined as the sum of kinetic energies of all its constituent molecules due to their translational, rotational, and vibrational motions, and the potential energies due to the interaction between these molecules. That our hands become warmer when we rub them together. Though there is no external supply of heat energy to the hands, the work done due to the friction between the hands makes them warmer. This implies that the internal energy of the hands, considered in this case as a system, is increased by doing work. That means that by doing work, we can change the internal energy of a system. There are two different ways of changing the internal energy of a system. One by allowing the system to exchange heat with its surroundings, and the other by allowing it to do some work. In thermodynamics, heat and work are the two modes of energy transfer to a system. Heat and work are not state variables. They depend on the path through which the system is taken. For example, consider a given mass of gas at an initial state described by P1, V1, T1. Let us plot a pressure versus volume diagram for the gas and identify the initial state of the gas as A in the PV diagram. Let us take the gas to a new or final state, described by P2, V2, T2, and identified by D in the PV diagram. We shall take the system from the initial state A to a final state D in two different ways. In the first method, place the container of gas on a hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure. After sufficient time, the gas may be at a new state, identified by P1, V1 T2, and represented by point B in the PV graph. The curve AB represents the process of changing the state of the gas from P1, V1, T1 to P1, V1 T2. Now, keeping temperature constant, compress the gas by placing a weight on the piston to the final state P2, V2, T2. This change in the state from P1, V1 T2 to P2, V2, T2 is represented by a curve BD in the PV graph. In the second method, compress the gas by placing some weights on the piston and change the initial state of the gas P1, V1, T1 to a new state represented by P2 V-T1. In the PV graph, the new state is represented by C and the process by the curve AC. Now place the container on the hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure to reach the final state P2 V2 T2. This process is shown by the curve CD in the PV graph. In this experiment, we have taken the system from its initial state P1 V1 T1 to a final state P2 V2 T2 by two different paths represented by ABD and ACD. Heat exchanged by the system in taking it from A to B and then from B to D is different from the heat exchanged in taking it from A to C and then from C to D. Even the work done by the system in taking it from A to D through ABD is different from the work done when taking it through ACD. In this aspect, the internal energy is different. Internal energy is a state variable. The internal energy of a system depends only on its state and is independent of the path through which it is taken. For example, in the experiment described earlier, let the internal energy of the system at its initial state P1 V1 T1 be U1 and the final state P2 V2 T2 be U2. Whether the system is taken through ABD or through ACD, the internal energy of the system in its final state remains U2 and is thus independent of the path followed. You have